Is that the sound of a Geiger counter? Is that glowing uranium ore under UV light? Do I smell radiation in the air? I'd better get out of here. Oh yikes, there's nuclear waste everywhere. Can't escape this stuff. Okay, alright, I'll stop pretending. But it is partly true though. We can't escape radioactive contamination. So let's jump right in. Today we'll be discussing novel cleanup solutions such as bioremediation, while briefly discussing current and future consequences of uranium waste on global ecosystems. We'll focus in on uranium sequestering biota and their mechanisms of bioreduction and biomineralisation. Lastly, we'll analyze the evident lack of global and large-scale bioremediation projects, and here we'll also address some notable drawbacks. Welcome to the nuclear age, where you have clean, limitless energy, as well as mutually assured destruction. Uranium mining in the United States began as early as the 1900s, although following the end of World War II and the first uses of atomic weapons, the demand for nuclear energy significantly increased. Many other countries, like those in the former Soviet Union and Western European countries, followed the US's footsteps, and uranium mining became a global and integral part of energy, defense, and industry during the mid-20th century. The US's peak uranium production came about in 1960, near the height of the Cold War. However, public support for civil nuclear technologies dwindled after disastrous events such as those at 3 Mile Island, Chernobyl, and recently Fukushima. The end of the Cold War and the subsequent collapse of the Soviet Union dramatically slowed the production of global uranium, and it reached an ultimate low in the early 2000s. Environmental consequences and concerns for the environment began to grow. So, what does this mean? What does the nuclear age mean today? And what are the implications of our past nuclear activities? And what do we do about the environment? Well, first, we need to talk about contamination. In this map, red and yellow dots represent uranium concentrations in major U.S. water sources. You'll notice the red dots clustering around much of the Rocky Mountain regions in Colorado, Wyoming, and Utah, as well as the southwestern states of Arizona and New Mexico. This isn't all that surprising, given that these locations were major sources of uranium mining for the U.S. in the 20th century. The blue clusters represent nitrate contamination, and most of this comes from excess nitrogen fertilizer and runoff in farming. Given the wide swath of this nitrate contamination along the Midwest and its close proximity to uranium concentration in the Rocky Mountains, we really need to brainstorm and act to contain these contaminants. This here is one of the former uranium mining sites in Rifle, Colorado. Historically, these mills produced much of the uranium needed to fulfill the U.S.'s rapid proliferation of nuclear weapons during the Cold War, and some sources claim upwards of 20 million tons of uranium tailings were concentrated in this area. In 1978, Congress finally recognized the environmental hazards of these mills at Rifle, and they passed the Uranium Mill Tailings Radiation Control Act. These mills were officially closed in 1984. However, today, uranium ore concentrations in the upper Colorado River Basin near this site are 200 times greater than background. Under the care of the Department of Energy Legacy Management, these mills offer insight into both the biotic and abiotic processes of bioremediation. First, we need to look at in situ uranium bioremediation studies, as these allow us to further study the microbe interactions. Uranium and organic matter have pretty strong interactions with each other, and the presence of organic matter acts as a kind of trap for aqueous uranium oxides. Hexavalent uranium is soluble and found in most contaminated water, and in situ studies show that native bacteria in soils can sequester away uranium through a series of chemical reactions, including the reduction of hexavalent uranium to tetravalent uranium and the formation of uranium ligand complexes. This experimental design, seen pictured here, shows that the injection of organic matter is required to stimulate aqueous uranium reduction. In the top circle, we see how uranium reduction is coupled with the oxidation of organic carbon. In the second circle below that, we see the solubility of hexavalent uranium versus the insolubility of tetravalent uranium. Native soil bacteria can interact with uranium in 4 different ways: bioreduction, biomineralisation, biosorption, and bioaccumulation. However, for the purpose of this presentation, we're only going to focus on bioreduction and biomineralisation. In bioreduction, soluble hexavalent uranium is reduced to insoluble solid tetravalent uranium, as certain soil bacteria can utilize aqueous uranium waste as an electron acceptor in their electron transport chains. Hair-like appendages, you can see this called pili in the upper left-hand corner. It's this very, very small squiggle. Are key in the reduction process, and they act as electrical conduits, and they can donate electrons from the processes of respiration into their surrounding environments. Uranium contamination is toxic to many organisms, so researchers hypothesize that the mechanism of the pili, or the function of the pili, give bacteria a quote-unquote reduction at a distance. They increase and maximize their catalytic capabilities while minimizing their exposure to toxic uranium. This essentially could be considered as a protective mechanism, allowing such organisms to survive radioactively contaminated environments. So our orange little friends pictured below here are notably called Geobacteria, and they are currently being employed in nuclear disaster sites such as Fukushima, showing great success at uranium sequestration. And put together, we can see that pili play both a part of cellular survival for these bacteria, as well as part of a larger, promising ecological cleanup technique. In biomineralisation, uranium metals are precipitated when hexavalent uranium combines with biologically produced ligands, including phosphates, silicates, and carbonates. This pathway also leads to solid uranium sequestration. Biomineralisation requires the addition of glycerol phosphate to contaminated environments. This stimulates native bacteria to cleave the glycerol and the phosphate, where the alcohol is used for growth by the bacteria, and the phosphate is allowed to precipitate with aqueous hexavalent uranium. Uranium biomineralization has a few advantages over bioreduction, including that it has a broader range of functional environmental conditions. This means that biomineralization can take place in both aerobic and anaerobic conditions, as well as across a pH of 4 to 8. Additionally, uranophosphate precipitations are inherently more stable, and they are less reactive to events that could reoxidize tetravalent uranium back into hexavalent uranium. However, glycerol phosphate is itself quite reactive. Think of it like chlorine by itself is super reactive, but chlorine-containing compounds like NaCl are very stable. Anyways, the rapid accumulation of glycerol phosphates into contaminated uranium waters could catalyze an uncontrollable accumulation of urinal precipitates. This is super precarious because a sudden surge could potentially block organisms from obtaining nutrients. For the sequestering biota, rapid accumulation may inhibit the production of phosphate ligands, thus stopping biomineralization altogether. The Oak Ridge National Laboratory in Tennessee is still conducting biomineralization experiments. However, biomineralization is a promising cleanup technology. Now that you know those two pathways of bioreduction and biomineralization, we can yield some very pretty and some very rare metals. Uranium is characteristically known to have a green or a yellowish tint. The main product at the rifle mills was called yellow cake for its bright yellow and powdery form. Even so, many of these uranium compounds fluoresce under ultraviolet light, which makes them even more pretty. The study of uranium orogenesis is particularly important as these compounds are an end result of reduction and mineralization. We see that there are many, many rock compounds containing uranium, and we can subgroup these minerals into whether they contain carbonate, oxide, phosphates, rare earth elements, silicates, sulfates, and vanidates. One of these minerals includes pitchblende, which historically was an integral compound for the discovery of radioactivity by Marie Curie in the early 1900s. However, given that historical aside, we need to understand that genome-scale uranium bioremediation is possible. In situ bioremediation experiments where we inject either organic material or glycerol phosphate to stimulate native bacteria, these experiments can take a significant amount of time to gather data, and with ever-expanding genetic technology, we can rapidly sequence and identify uranium-uptaking organisms. Microalgae belonging to the family of Chlamydomonas is of particular interest due to their extremotolerant genes. They're pictured here in gray. Because these genes permit them to tolerate low pHs and high radioactive metal concentrations. Preliminary studies suggest that they can uptake uranium at about 7.9 milligrams per gram of biomass, and this suggests that Chlamydomonas species can rapidly reduce uranium-6 into uranium-4, forming a solid, more stable state. Ultimately, we need genetic sequencing to observe and document the organisms that can survive these extremely harsh, radioactive, contaminated environments. And we need to first create a large gene library of organisms that can uptake uranium. And from there, we need to isolate particular individual genes. CRISPR gene editing tools will come in very handy because we can use them to cut and insert these genes into select organisms. This could drastically maximize bioremediation capabilities and efficiency. Blended with the knowledge of the biochemistry mechanisms of bioreduction and biomineralisation, we can better understand the genetic components of specific uranium sequestering biota. Given the long startup and result time, bioremediation of uranium waste is not yet very cost-effective. The U.S. Department of Energy predicts more than $16 million to clean up uranium mines that produce up to 500,000 tons of materials. And if you remember, the rifle site in Colorado, and if sources are correct, had almost 20 million tons of tailings, to which the U.S. Department of Energy predicts over $500 million are required for cleanup costs there. It is also worth noting that many of these lands, these contaminated lands out in the Rocky Mountain regions in southwestern United States, originally belonged to many indigenous communities, some of which still live there. And much of the cleanup task is put on their shoulders, and some of these communities cannot afford the extremely high costs of bioremediation, and this is another big reason why we don't see bioremediation on a large-scale model. On top of that, costs of bioremediation are even higher if we're using genetically engineered organisms. This again highlights that we need to gather more genetic data first so we can further understand the microbiology behind uranium sequestration and develop more efficient and cheaper genetic modification methods. Additionally, there is no standard endpoint in which to measure bioremediation performance on uranium tailings. Definitions of clean vary by country, and environmental protection agencies may be lacking in some areas. In Japan and Russia, these entities are important in the cleanup of disaster sites such as Fukushima and Chernobyl, but it must be understood that these perspectives and interpretations of uranium bioremediations may significantly differ from those in the United States, both for reasons of non-standard measurements, but also for various environmental conditions, such as the amount of organic matter already present in soils and the geological timescales of chemical weathering. Lastly, uranium bioremediation is set back by inadvertent ecosystem disruptions, such as accumulation of other toxic heavy metals. But organisms may successfully sequester away uranium. Contaminants such as lead, cadmium, and mercury may still pollute ecosystems. These can build up and enter food chains, potentially posing a significant risk for humans. Bioremediation, of course, is not limited to just uranium. The use of multiple organisms that each target a certain pollutant may be a solution to avoid the unintentional accumulation of other heavy metals. In conclusion, 20th century geopolitics kickstarted many nations to rapidly acquire uranium materials, and the consequences of such actions are still alive today. For both bioreduction and biomineralisation, the process in which to get stable and solid uranium compounds is still pretty turbulent and requires more research, particularly of that in the genetic sector. Moving forward, we also expect in situ experiments to contaminated sites to continue publishing data and knowledge. We expect benchtop experiments to help synthesize and better direct field studies. Future ecosystems and future industries rely on the highly potential partnership between uranium contaminants and uranium sequestering bacteria. If we understand the mechanisms as well as the projected implications of uranium bioremediation, we are better equipped to develop civil nuclear technologies that have effective cleanup and preventative contamination strategies.